Hi everyone, thanks for coming to the first talk of the year, focusing so many new faces. Let's go before through that door on the side. Today's talk with Dr Anke Arentsen from the University of Cambridge. Her talk title is up on screen there. It's about galactic archaeology using young stars in the Milky Way. I hope you all enjoy. Come on, guys.
Yeah, so it's not actually young stars; it's the oldest stars in the Milky Way, which is very important, but that doesn't matter. Yeah, so thanks so much for having me and for being here. I'll talk about galactic archaeology with the oldest stars in the Milky Way, and I'll go through the various parts of this title. I hope I pitched it more or less right for the audience, but I also know that's kind of a mixed audience. So if there's something you really don't understand or don't follow, please don't hesitate to ask and interrupt, because then it might help you to understand the rest of the talk. So what I'm studying is the Milky Way, and this is an artist's impression of the Milky Way. Because we're in the Milky Way, we cannot take pictures from the outside. So all we have is these artist impressions. Just to kind of give you a rough idea, we are over here about 2/3 to the way of the center, in the disk, in where the spiral arms are. Throughout the talk, I'll use so yeah, the distance from the sun to the center is about 26,000 light years, but astronomers typically don't use light years. We use a different unit, which is kiloparsec, which is about 3 light years in a parsec. But all that matters for this talk is kind of the relative scale. So we're about 8 kiloparsec from the center here. So the Milky Way is a galaxy among many other galaxies. It has about 200 billion stars in it. The sun is one of them. And here in this map of stars, it's about 1% of the stars in the Milky Way shown on this map that has been observed with the Gaia space mission. So here it's not a photo, it's kind of a map of the brightness and color of all of these different stars. So you can see it's pretty flat. That is this whole disky area. In the middle, you have a little bit of an extension. That is kind of this area with the bar and vertical extension, the galactic bulge. So about 99% of the stars are in the Milky Way, are in the disk of the Milky Way. But there's also about a 1% of stars that are spread in a spheroidal distribution around the Milky Way. So not in this flat distribution, but much more extended than the disk as well. So this is what we call the galactic halo. So how do galaxies form? We have this beautiful spiral galaxy that we live in today. But at the beginning of the universe, there's no galaxies. You just have a mix of gas and photons. And then after a while, you have the first stars that are forming. This is a few 100 million years after the Big Bang. And these first stars were likely very massive because they have to form from hydrogen and helium alone. There's no other elements yet. And it's hard to form smaller stars. So you get really big stars that explode very quickly. And then you have about 13.7 billion years of evolution until you get to the Milky Way today. And along the way, you gradually form larger and larger structures. So in this video is a simulation of formation of a galaxy. So you can see very small bits that are growing and coming together. So these are small clumps of stars and gas that are coming together to build a larger and larger galaxy. So these small clumps, we call them kind of the building blocks of a galaxy. And soon you start to see one main galaxy or thing in the video. And then just smaller things are still accreting and contributing. And then at some point you start forming the disk, a flat structure, but you might still have more of the smaller things that come in. So most of the stars in a galaxy are in the disk. So it's formed inside the main system. And then the smaller things that are still coming in, they're forming the galactic halo. So to kind of summarize it in this way, you start with a bunch of small things, and then you gradually grow larger. Until you have a galaxy like the Milky Way, or very different kinds of galaxies. So what I'm interested in, one of the things I'm interested in is these first galactic building blocks. The first things that started coming together that brought in the first stars that in the Milky Way, not the things that came in later, but the very, very early things. So these are the first galactic building blocks. So how can we study galaxy formation and early galaxy formation in specifically? So one thing we can do is we can look at the very distant universe, the redshifted universe, and directly look at galaxies as they were a long time ago. So this is what currently is very, very active topic of research with the James Webb Space Telescope, looking at very, very high redshift, very distant universe. And then you have these little blobs that are little galaxies. And so you can do that, but then you just have a few pixels to work with. The other thing you can do is you can look locally inside the Milky Way and look at stars that are still around from this very early time. So look at really old stars. And this is kind of what we do in galactic archaeology. We're trying to find the local fossils or remnants from the early universe and try to learn something from them about what the universe was like, what the early galaxy was like. So that will be the focus of this talk, the Galactic Archaeology side. So why can we do this? So stars have different lifetimes. If you have a very big star, like this one over here, it will explode quickly in terms of, in astronomical terms, about 10 million years it might live and then it explodes. And with respect to the age of the universe, that's not very much. You can have, many generations of these until you get to today. But as you get to smaller and smaller stars, they live for longer. So stars shine because they do nuclear fusion in their core, and big stars just go much more quickly through their fuel and then they explode. Whereas the smaller stars, they're much slower in going through their fuel, and they can live for much longer. So then if you get to these very small stars on the left-hand side, the smaller stars, they can live for hundreds of billions of years. So if they formed, just after the Big Bang, they would still be around and they wouldn't have changed very much. So this is what we do. We look for these kind of stars, these very small stars that are around from the very, very early universe and that are still here today. So how can we do that? So as I mentioned, in the early universe, so before any stars form, you just have hydrogen and helium and a little bit of lithium. So this is your entire periodic table. But then you have the first stars forming and they explode. And in the lifetimes of the stars, they form new elements. And then when they explode, they can form even higher mass elements. And then there's also there's various processes that can make all of the elements on the periodic table. So this is maybe the periodic table that you haven't seen it colored this way before. This is not a chemical coloring, but it's an astronomical coloring. So where do these elements come from? So for example, the yellow comes from dying low mass stars. So smaller stars at the end of their lives, they kind of have strong winds that go out and they slowly kind of turn into a white dwarf. And in that last phase, you form these yellow elements. Then you have the green, which is exploding massive stars. So supernovae, the very, very big stars, they explode very quickly. So that is all of these mostly green elements. Then you have exploding white dwarfs. These are, so a white dwarf is the end product of a low mass star. And it can explode if it's in a binary system. It doesn't really matter, but it's a different kind of channel and it produces different kinds of elements, or mostly these here. And then you have some more exotic elements that we think there's various ways of making them, but one of them is merging neutron stars. So these are kind of these heavy elements down here. So all of these elements are produced on different timescales, and the first stars are making the first elements. So we go back to this picture of the universe, the early universe, and today, time going in this direction. You have the first stars forming here, and then over time you have more and more elements building up. So stars form from gas enriched with metals or any kinds of elements by previous stellar generations, and they do not really change their surface abundance over time. So the gas that they formed from is kind of what they still look like today. So that's how we can tell something about the chemical composition in the early universe. So if a star forms really early on in the universe, it's a metal core star. In astronomy, a metal is everything heavier than helium. exactly for the reason that I just showed. That's the stuff that gets made later on. So my apologies to the chemist, but I'll keep using metal for this concept. Yeah, so we have a star that is born very early on, it's metal poor, and it will still look metal poor today. And if a star is formed later, it's metal rich. And then in the Milky Way today, we have a mix of these stars. We have metal poor stars and we have metal rich stars. So we have stars that were formed at this time and then stars that were formed at this very early time. So that means that the Milky Way is a local kind of time machine for the entire history of the universe, at least locally. So we can learn something about the chemical enrichment. So throughout the talk, I'll use the concept of metallicity, which is how many metals a star has, or how many heavier elements a star has. So we're using it on a logarithmic scale where the sun is at 0. And we use iron as a trace element that's kind of representative for all metals, partly because it gets kind of linearly created over time, and partly because it has lots of spectral lines that you can measure. So it's relatively easy to determine. So then we have here a cartoon representation of the disk and the center of the Milky Way, the galactic bulge. And about 99% of the stars are in this component, and they're in this metallicity range. -1 means it's a tenth of the abundance in the sun. And then here you have some more metal rich, but it doesn't go much beyond. The sun formed relatively recently, so it's quite metal rich. And then as you go to lower and lower metallicity, so -2 means 100th of the metals in the sun, -3 means 1,000. So this is about 1% of the stars in the Milky Way, and they're mostly distributed in the galactic halo, not in this flat disky component, but here in the spheroidal distribution. And these are the stars I'm most interested in. So this is kind of older to younger stars. And these are the very old stars that can teach us about the early history of our galaxy. Yeah, so if we look at these stars, they're mostly in the halo, but as I will show, they're also in the very, very center. It's kind of the center of the halo, but also overlapping with the disk and the bulge and all of these components. So the halo kind of formed first and is still sometimes, when something comes in, it's still being added to. And the disk is formed later, so it's mostly younger stars. So then how can we tell the metallicity of a star? So what we usually use is spectroscopic observations. So this is the spectrum of the sun. And what you can see here are absorption lines of specific elements. So these elements are in the atmosphere of a star. This is the part of the star that hasn't changed since basically when it was born. So it's tracing the surface abundance. And so these elements are absorbing the light that the star emits. And for example, you can recognize here's 2 strong calcium lines, there's hydrogen lines, there's iron lines, there's all kinds of lines. All of this that is not just pure color is coming from some element. So we can use the spectrum to measure how many metals there are. So this is again the spectrum of the sun, now shown how I usually look at spectra. So this is the wavelength, so the color, and this is the brightness, or how much light comes from the star at a given wavelength. And here again, you can see these lines that are showing up as dark lines in here. Here they are dips in the spectrum. So what we can do is we can measure kind of the width and the depth of these lines, and that tells us how much of this specific element is in the atmosphere of a star. So you can measure how much calcium, how much iron, and all of these things are in the atmosphere of a star. So as I mentioned, the sun is relatively metal rich. So all of these wiggles that you see here, they all come from absorption from different elements. So if you have a metal poor star, it looks a bit more like this black line. So this is one of the most metal poor stars that we know of. So this is the sun again in gray. You see all of these lines, and this metal poor star, you basically see only these big lines are hydrogen. Every star has hydrogen. And then here is a little bit of calcium, and that's the only thing you can see, at least in this part of the spectrum. So from the spectra, it's relatively easy to tell whether a star is metal rich or metal poor. And especially this region is either very strong lines or almost no lines, but still a little bit of calcium here. So you can kind of use this region is very sensitive to the metallicity, even for ultra metal poor stars. But spectroscopy is quite resource intensive. It takes a lot of time to get a spectrum for a star. You have to have big telescopes, big instruments, and metal poor stars are rare. So only 1% of the stars in the Milky Way is in the halo, and of those, only a smaller percentage will be, among the most rarest metal poor stars that we care about. So you have to do some kind of clever selection, pre-selection, before you do spectroscopy. You can't just do that for every star in the sky and hope you get lucky, although we are getting to the point where we almost can do this. But I'll mention a bit more about that. And instead, what we do is we use imaging or photometry of stars, which is a lot cheaper. So in astronomy, you usually image in different filters, and then you combine these filters to get a color for your image or for a star. But these filters, the typical ones, they're quite broad. They cover quite a big wavelength range. And what we do in the survey that I'm a part of is we use a very narrow filter, this one, that is centered on these very strong two calcium lines that I was showing before. So, and then we use this to image the sky and get kind of a sense of the metallicity. And how this works, so here's again this kind of filter curve, this short wavelength range. These two big dips are the two calcium lines. So this is for a star that is as metal rich as the sun. And then as we go to lower metallicity, so 1/10 or -1, you can see that these lines kind of narrow. And then as you go to lower metallicity and lower metallicity, these lines become narrower and narrower. So the way we use this filter, if there's not a lot of light that passes through, that means that these lines are very strong and they're blocking almost all of the light. So if a star looks faint in this filter, it's probably metal rich. But if these dips are very small, the star will be very bright in this filter. So that's kind of what we use to an estimate of how strong these lines are, but just with imaging. So this is in the Pristine collaboration. It's a sky survey of images in this calcium H&K region. So we're imaging, in one image, you get about a square degree of the sky, you get hundreds or thousands of stars. And very, very quickly, in 100, 200 seconds, you get a lot of these stars. And then you pick the most interesting ones to follow up with more expensive spectroscopy. So the telescope we use is this one. It's the CFHD, the Canada-France-Hawaii telescope on Hawaii, where the weather is really excellent and you get really good quality of your images. And this is just some pictures of the collaboration. This is one we were all confined to our homes and we're having meetings on Zoom. And this was last year, much more pleasant on La Palma, where we had our latest collaboration meeting. And not just because it's a nice place. La Palma, of course, is a nice place, but there's lots of telescopes there. It was just one reason why we went there, because we have some connections with some telescopes there. For example, this is the Isaac Newton telescope on La Palma. It's a relatively small one with 2.5 meter mirror in size. And we've used it extensively to do first low quality spectroscopic follow-up of the most exciting candidates. And we did that a bit last year, or about 2 years ago. So in 2021, 2022, we had an observing program where we had 20 nights on the telescope, but we had a lot of technical issues. So I'm just sharing this because this is the life of an astronomer, an observational astronomer. We had problems due to COVID. We couldn't go. The telescope was closed. They had to do it for us. Then there was storms where the telescope couldn't be opened. It was too dangerous. There was dust from the Sahara. You have wind coming from the Sahara to the islands, and then you cannot open the telescope because dust can damage the instrument and the mirror. Several miscommunications between people. That is what happens. You say you want one thing, you get another thing. And then also, unfortunately, we were there at the time that they had this volcano that was going off. So we had an observing run, and about 2 days before we were going to go, the volcano started erupting. So we asked, should we go? Is it safe to go? And said, yeah, it's fine. The wind is in the other direction. Just come and observe. It's all fine. And of course, while we were there, the wind changed and came right towards the observatory. So I'm laughing about it now, but it was actually quite scary. And this is from the telescope, just somewhere over here. We could see the the smoke rising. Yeah, so then of course also you can't observe because there's ashes and dust, and then we had to be evacuated as well. So that's just a story from the life of an astronomer. But in the end, last year we had a lot better luck, and we had lots of observations that went very well. So the Pristine survey, where are we looking? So this is our current footprint on the sky, which means where we're looking in yellow. So these regions, and we're still observing, which is why there's a bunch of gaps. We're still filling in more gaps with the telescope. So we're mostly looking away from the disk, because I mentioned the disk is the most matter-rich part of the Milky Way. So we're kind of looking up towards the galactic halo, which is the most metal-poor part of the Milky Way. And we're aiming to observe most of the northern sky. So from the telescope, you can mostly see the northern sky. So as you can see, there's also this bit in the middle that's very disconnected. And I'll say a bit more about that in a minute. So this is all of the papers over the past 5-6 years from the Pristine collaboration that is based on this data and follow-up data. If you're interested, you can have a look at our website, but these are mostly very technical publications, but on a very, very large range of topics. So then what's going to be the focus of the rest of the talk is the Pristine Inner Galaxy Survey, or PIGS, which is this region, focusing at the very, very center of the Milky Way. So this is the PIGS logo, which was painted by my mom. And yeah, so this is the region that we're looking at the very center. And we're also covering various topics in our publications. So what is there to see in the inner regions of the Milky Way? So this is, again, an artist's impression of the Milky Way. You can see these very dusty lanes in the disk, and then this is the galactic bulge, so it's extending from the center. So you can already see observing the inner galaxy is not easy from our vantage point within the disk. You have to look through all of this dust to get to the center. So that's one reason why people haven't really searched for these metal-poor stars in the center for many years, and it's only become feasible in the past 10 years or so to do this. So the main component is called a boxy peanut bulge. You can kind of see here this kind of peanutty shape. And we think that this formed from the galactic disk, from an instability in the disk that made it extend to higher vertical heights. And we can tell this from the fact that it's mostly metal-rich and it's rotating around the center at the speed that you would expect for kind of stars originating from the disk. So in this region, most of the stars are part of this component. So if you randomly select a star, it will be metal-rich most of the time. So then we also have the galactic halo. So this is this component mostly made up from small galaxies that are accreted early on and still, and some stars that kicked out of the disk. And as this has the center, the halo has a center which overlaps with the galactic bulge. So there will be some of these metal-poor stars there. And then there's also been a question for a long time whether there is a much more concentrated population in the center of the Milky Way that formed very, very early on. So in this talk, I will call it the proto-galaxy, the very, very early formation of the Milky Way before there was a disk, and the very early building blocks. And some open questions still today are whether these come later from accreted small systems, or most of these stars formed inside the big Milky Way building block. So if it's that difficult, why are we looking for metal-poor stars in the center? Why don't we just look at the halo? So there's various reasons, and one of the main ones is that galaxy formation models suggest that the central regions of galaxies form first. So this is the part of the Milky Way that started forming us, and this is where you can find the oldest metal-poor stars. So far I've said that metallicity and age are kind of connected, but it's not linearly. In some places, metal-poor stars are older than other places, and this is kind of what can be seen in this graph from a paper from a few years ago. So this is just the spatial distribution in kiloparsec, and the darker the color, the higher the fraction of really old metal-poor stars. And you can see that in the center, it's very high. Also in the outer regions, but also in the very center. So that's one reason to look for these metal-poor stars there. And then there's still a bunch of open questions. For example, where did the metal-poor stars in this in this region come from? Are they the same as the ones that we find in the rest of the halo? Or is there something different about them? And what kind of building blocks that contributed? Is it mostly one big one? Is it a bunch of small ones? This is still an open question. And then also, the more metal poor you go, the closer you get to the first stars. You can actually learn about the first stars. And they might have been different in different environments. So that's another reason why we want to find these really metal poor stars also in the center of the Milky Way. Yeah, so again, this is where we look in the inner galaxy. We kind of have a cutoff over here because we're observing from the northern hemisphere. So that means we can't go much more in that direction. So this is the imaging that we have, this calcium HK imaging. And then from that, we select promising candidates and we do spectroscopic follow-up. In our case, we used a telescope in Australia, the Anglo-Australian telescope, which we could take 400 spectra per pointing at the same time, which is a big advantage of sort of going one by one. And we can do this because the inner galaxy is just so densely populated in stars that it's easy to fill all of the targets. So this is an example from some of the spectra that we received from a telescope. So here is a star at higher metallicity, and then we go lower and even lower. And you can see that you go from lots of wiggles to less and less wiggles. So these spectra are relatively low resolution. That means you can get limited information from them, but you can easily get the metallicity because you can by eye see the difference. So other factors in shaping the spectra are also the temperature of a star and its evolutionary phase, but we will ignore that for today. So this is just 3 examples. In total, we observed 13,000 stars. And this is the distribution in the metallicity. So here in yellow and gray is kind of, you have a standard survey looking at the center of the Milky Way, just randomly select stars. They're going to be metal rich like the sun or a little bit more metal poor, but there's almost nothing in this regime of the very metal poor stars where we're interested. But then in pigs, we have this pre-selection, so we're much more efficient in picking up these metal poor stars, and we actually start having statistically significant samples that we can use to study the population. So we have about 2,000 stars below -2. So then we have the sample. What can we learn about the metal poor in a galaxy? So I'll focus mostly on the dynamics of these stars. How are they moving? And then if I have time, I'll talk a little bit about the chemical compositions towards the end. So I'm highlighting pigs because it's the project that I built and I worked on, but there's a lot of other work in this area as well, and I'll highlight a little bit later. So again, this is the artist's impression of the Milky Way. We're about here. This is where the central region is. And the question of these stars that we found in the inner galaxy is, one question is, do they stay there or are they just passing through? So these are just some possible orbits of these stars. They could be going out all the way in the halo and just coming in for a little bit, going through and moving back out. And this was the expectation of a lot of people before we started finding these stars, that mostly what you get is kind of the extension of the halo, stars that are just spending a little bit of time there and then moving back out. And then another question is, how are these stars moving? So do they move regularly, like these little pigs? Or are they kind of on random orbits, and do they not move coherently like the one on the right? And this was also not a question that we hadn't have a clear answer to. So how do we get the dynamical properties of these stars? So first, what you need to know is the distance. How far away are these stars from us? Which is not trivial to determine. And then what you need is the velocity along the line of sight. And then what you need is also the velocity on sky. How are the stars moving on sky? And if you have all of these different things, you can reconstruct its position and 3-dimensional velocity in the Milky Way. So how do we get all of these different parameters? So we get the radial velocity, so this component along the line of sight, from the pig's spectra. So here I've shown 2 spectra with these are 3 calcium lines in a different spectral region than before. And they're supposed to lie on the gray lines. This is where we know that calcium absorbs or emits. But these spectra are not, and that's because they're either redshifted or blue shifted, because they're moving. So if you have a blue shift, the star has a negative velocity, and if you have a redshift, it has a positive velocity. So this is how we get the radial velocities along the line of sight from the spectra. And then the others, the distances and the proper motions, were very, very dependent on the Gaia mission, which is a mission that in space, that a satellite that scans the sky many, many times and looks at how stars are moving very, very precisely. So Gaia has all kinds of parameters that it gives. Most importantly for us is this one, that it provides for 1.5 billion stars. It provides how a star moves across the sky and more or less the distance of the star. So how does it do this? It looks at the star many, many times, and this is coordinates on the sky. Doesn't really matter what they are if you're not familiar with them, but the star is moving, is apparently moving on the sky as you make observations. And this is partly because the star is actually moving. This is called the proper motion, and partly because of the parallax, which means if you're on one side of the sun, you observe a star from this direction. If you're on the other side, you observe from that direction, and it kind of wobbles on the sky. And this is how you can get the distance for a star. So this is now available for lots and lots of stars, and this is really a game changer. Before that, it was really hard to get distances and the motion on-sky motions for stars. So then we combine all of these different things. You know where a star is, you know how fast it's moving. But what you also want to know is, for example, how far out does the star go? How elliptical is its orbit? How round? How not round? And for that, what you need is a model for the potential of the Milky Way. So where is the mass? How much mass is there? How is it distributed? And if you have this information, you can compute the orbit for a star if you have the distance and the velocities. So then you integrate these orbits so that how a star moves, you can get its epicenter and pericenter, which means the closest approach to the center and the furthest. You can get how eccentric the orbit is, and also how far above the plane. Is it like in the plane, like a disk star, or is it kind of at all kinds of angles, like halo stars? So what do we find for the pig sample? So this is the orbit of the sun, or just an artist's impression of it. It's relatively circular around the center of the Milky Way. So this is a circular orbit, has low eccentricity, and a radial orbit has high eccentricity, and it's much more squashed, and it's very elliptical. So what we find in pigs is that we have quite high eccentricities for our metal poor stars. So this is kind of represented in these kind of orbits. They're not flat and circular, but they're kind of random motions. And it's slightly different for metal poor and very metal poor stars, which you can see here. But in general, they have very, very similar behavior. So this tells us these stars have high eccentricity. That's one thing we know. And also what we find is that there are mostly random orientations with respect to the disk plane. So that means they're not all moving in the disk plane, they can also move outside at a different angle. So then what about the epicenter? What about the maximum radius of the star? Are they staying in the inner galaxy, or are they going out like really far? And what we're finding is that most of them are actually staying in this very inner region of the Milky Way. So this is the distribution in epicenters, and you can see 5 kiloparsecs here, which is more or less here in the artist's impression. Most of the stars stay within that region. So that means locally at the sun, if you just do local observations, you would never find these stars because they're not in our volume where we observe. So that means you need dedicated surveys looking towards the inner regions to study this population. You can also see that the very middle poor stars in blue, they have a bit of a larger tail towards these higher epicenters. And this tells us that they're probably a bit more like a halo population than the other ones, but they're still very, very centrally concentrated. So highly eccentric, very centrally concentrated. And then what about the regularity of their motions? Are they going around the galactic center kind of together as a group, or do they have no net rotation, no net angular momentum? So what we find is that in this graph, we're showing the metallicity as a function of the radial velocity, where here at 100, you have where typical bulge stars are, like metal-rich stars. And then here you have no rotation at all. And we find that as you go to older and older stars, you have lower and lower rotation. So these stars are kind of going almost as fast as, you know, typical bold stars, but then these stars are going a lot slower. And this is also something that couldn't really be seen before until you had these large samples of stars in the inner region. So then to summarize what we've learned from this work, which is work in progress, is that these stars are very confined to the inner galaxy. They're slowly rotating around the center, and they're very highly eccentric orbits. So from a different survey, we also see that they're on the sky, all in the same place. So this is galactic longitude. So this is the galactic center is here, and this is along the disk plane, and this is if you go in the other direction. And this is a distribution of metal poor stars, where yellow means a higher concentration and purple means a lower concentration. And this is from work using Gaia data, but actually getting metallicities for all of these Gaia stars homogeneously. And then you can see this population kind of pop out. This is, I guess, a similar, if you more or less convert it to kiloparsec, it's also about 5 kiloparsec large on the sky. And you can see that here there's a stripe missing. And this is all because of dust extinction that blocks the light, and we don't get good observations in that region. So overall, this population kind of looks like a halo population, but more central, with faster rotation than the rest of the halo, and also with higher eccentricities. So it's kind of similar, but there's also some differences. So then what are the suggested origins of this population? We think that it's kind of the early chaotic proto-galaxy phase of the Milky Way that we're seeing. So this is before the disk existed, when the first large building blocks came in to build this population. And then over time, you slowly start building a gas disk and start forming stars in the disk and start forming more metal-rich stars. So this is some figures from a galaxy simulation that is 2 different galaxies from 12.1 gig years ago, 11.5 gig years ago, and today. So here you can kind of see this very clumpy beginning state where you have big clumps that are kind of the building blocks that are coming together, a bunch of small ones. And as you go one step further, you already see that there's a bit more of a central concentration, but still stuff is coming in like from all different angles, this very chaotic phase. And then today, this is how these stars are distributed in space. And this very centrally concentrated, kind of spheroidal. And they also find that it usually has a little bit of rotation. So probably what we're seeing is the result of the very first building blocks of the Milky Way, which is really exciting. So one question that I still don't know the answer to, and I think will take some more years to figure out, is where this rotation comes from. So we find that on average, this population is rotating a bit. And why is it so high in eccentricity? So there's a few suggestions. So the rotation might be if these are formed in some sort of proto-disk, so very, very early version of the disk where you have stars that are rotating. But there's not a lot of evidence for that yet. Or maybe in this very early chaotic phase, you have all of these building blocks coming together, and there might just be some leftover angular momentum from this phase, that you have a few more building blocks coming in from one direction and from another. That means you have a little bit of spin left over in this population. And then finally, I haven't mentioned it much, but in the inner galaxy, you have this bar structure, which is a very elongated structure with very highly elliptical orbits. And actually, this bar is quite massive and can influence the orbits of stars in the inner region of the Milky Way. And it can actually make them more eccentric, and also it can capture them and kind of sweep them up and make them rotate a little bit around the galactic center. So these are still all things that are being explored. So just a little break point. How did we get to this point? All of this knowledge that we have, partly personally and partly what we've learned from the rest of the literature. So the pigs story started in 2017 when it was just a few months into my PhD. And I started discussing with my advisor, what should my main project be? And she said, well, how about we look at the bulge? And I was very enthusiastic. I was like, yes, let's do it. not realizing why people hadn't done it before, because it's really challenging to do. But in the end, it was really good. It was the right time. We had the right opportunities to start doing this. So then we started writing telescope proposals. You write a proposal, you say, I would like to observe this for these reasons, for this many hours. And luckily we were successful and could do quite quick follow-up. And then after half a year, we had the first data. And then there's a bit of a gap, because that's when the difficult part starts. You're doing the data analysis, you're writing more proposals to get a larger sample, presenting at conferences, which then gives you ideas on what kind of papers to write. And writing the papers, lots of help from collaborators, and coming up with a name or anything for the project. And then after another 2 years, we had the first paper of the project accepted, which was about the rotation around the center, but for a much smaller sample than we now have. And then the second paper was accepted just before I defended my PhD, for almost 4 years later. So you can see this is, these things take time to build a project. You have to propose the data, you have to get it, you have to show that it works, and you get more data, and then you write the papers. So yeah, this is how many observational projects work, especially if they're large surveys like this. And then, yeah, I started my first postdoc, got the third paper accepted, started the second postdoc, and I'm still working on the last things that I showed you today. So it's a project in progress, and it's been fun, but lots of ups and downs along the way. So I've mostly focused on pigs, but it's definitely not the only project looking at the metal core inner galaxy. So here is just a compilation that you don't have to read, but just to show how many works there have been on the inner galaxy. So lots of these over here are using kind of small numbers of stars, or small numbers with really high quality observations, and we're kind of contributing to that. And then also lots of simulation work to kind of explain the stuff that we're seeing in the inner galaxy. So it's a very active topic of research, this early phase of galaxy formation that we're now slowly starting to see come into focus. How much time do we have?
15 minutes.
15 minutes. Okay, great. So then there's a kind of a second part of the talk that goes more into what else we can learn about these stars. I've just focused on how the stars move mostly, but how can we learn more about their origin? There's only so much that we can learn from metallicities and dynamics only, and there's so much more information in the stars. So that brings me back to the periodic table here. So far, all I've used is hydrogen and iron to get the kind of metallicity for a star, but there's all of these different elements that can teach you more about the origins of stars, where they formed, what kind of environment they formed in, a small system, a big system. And all these elements can tell you about that because they formed on different timescales. So these different channels, these different colors, as I mentioned, they're formed on different times. And I'll try to clarify that a little bit more. So you have stars of different masses. You have exploding massive stars that's almost instant. You have these stars that maybe live for 10 million years, and then they explode as a supernova. And then they give their elements back to the interstellar medium, and the next generation of stars can form from that material. So it's very quickly enriched, and you can see this already in the first next generation of stars. So then these dying low mass stars, they're kind of in this range, A, F, G or so. These are the winds of these dying stars. They're not exploding, but they are shedding their outer layers. And in this process, they produce elements that are these yellow elements. So they're a bit delayed. They take time because these smaller stars take longer to evolve. So if you have the first stars, they explode. If you have a next generation of stars, these kind of elements are not yet contributing, but these are. So you should see that in the pattern of these stars. And then you also have these exploding white dwarfs and merging neutron stars, and they're even more delayed. These are systems that are in binaries. So there's two stars in the same system. And either two neutron stars, so neutron star is what forms after a massive stars have gone supernova, So it means that both of these stars must have gone supernova, they're spiraling around each other, and it takes time for them to spiral in and merge and then produce these elements. So there's an even longer delay for these kind of elements to contribute in the universe. And similar with the exploding white dwarf stars, they're also in a binary system, and if they accrete from their companion, they can go supernova and explode. So back to this periodic table, I've now circled some of the elements that are often measured in spectra. So it really depends on how easy are their lines to detect, how strong are their lines, what kind of spectra do you have. But you can see that these elements cover, the green ones, the blue ones, the yellow, and the orange. So we're kind of probing all of these different channels. And this is where it gets complicated. If you can take ratios of the different elements, you get kind of a certain timeline. But it's not important to really grasp the details of it. It's just the idea that you have stars from different channels producing on different timescales. Let me skip this one because I have a little bit more time. So that was a summary slide if I didn't have time, but I do have time, so I'll go over in a bit more detail. So what can we learn from the elements? So for example, in this range between metal core and very metal core, one thing that we can do is we can distinguish stars that were accreted from small systems from stars that formed in situ inside the Milky Way. Also, if you use the dynamics of stars. So stars in situ in the Milky Way, they formed in this very large galaxy, which has very quick star formation and enriches very quickly, just because you have a lot of stuff going on. Whereas accreted systems, they're usually smaller. You have a few supernovae, you have a bit of a break, you have more supernovas. It's a bit of a slower pace. So you can imagine that these ratios of different elements will be different for these in situ and accreted stars. So it doesn't matter too much if you don't grasp the details on this. This is just a sample of stars as a function of metallicity, and one of these elemental ratios. This is aluminum. Aluminium? What do you say in the UK? Aluminium. I'm sorry. Yes, and that is an element that mostly forms from exploding massive stars, so it forms very quickly. Whereas iron, which is here in the ratio, it forms almost equally from these white dwarfs, which take a longer time, and these massive stars. So this ratio kind of splits stars that are in the disk, so formed inside the Milky Way, and of these stars that were accreted from small systems. So you can use the kind of chemistry to split them from each other and kind of identify, oh, these were all coming from external systems and these were all formed inside the Milky Way. So one thing we found is that there's, through the chemistry and the dynamics, that there has been a big merger event that happened about 7, 8, 9 gig years ago that came into the Milky Way and distributed its stars throughout the galactic halo. And they're kind of currently located all over the halo. They're not really coherent in space. In this simulation they are, but we think that they're actually all over the sky in all distributions. But they still have some memory in their dynamics and definitely in their chemistry. So if you get the abundances for these stars, they're different. They're exactly this blob, this big blob of stars that you see here is this big merger event that happened some time ago. So unfortunately, it's a bit more challenging at very low metallicity for various reasons. One is that it was actually more similar in bigger and smaller systems, so you don't see that strong a difference. And it's also more challenging in the inner galaxy, because the inner galaxy formed first from building blocks that are all kind of forming at the same time. So you don't really have things that already took a long time separately to evolve from the Milky Way. Yes, so that's some of the things we can learn from these kind of intermediate metal core stars. And then if you have really low metallicity stars, you're getting closer and closer to the era of the very first stars. So this metal-free stars that formed. So they're the descendants, which means they were born from the gas that was polluted by the supernovae of the first stars. So if you get the abundances, that actually means you're learning something about what happened in the very first stars, even though they're not around anymore. So for example, we can kind of try to estimate how massive the first stars were, how they exploded, and how quickly that galaxies enriched in their elements. So one thing we found among the most metal poor stars, I'll just focus on one. There's a lot of things that I could focus on, which is that there's a lot of stars that are really rich in carbon for some reason. As you go to lower and lower metallicity, this is shown here again, and this is now the carbon abundance. This is 10 times as much as the sun, 100 and 1,000. And you see this blob of really carbon-rich stars away from kind of the main blob of stars. And they become more and more frequent the closer you get to the first stars. So that means they're likely telling us something about the first stars that was different about supernovae today. A supernova today wouldn't make that much carbon, but apparently the first supernova did. So then what you can do is you can model the whole pattern of abundances and kind of match it to supernova models and see what kind of model matches best. Is it a 10 solar mass star or 100? And so you can kind of reconstruct what these stars were, the first stars were like. Yeah, so this is what I've been saying, that these most metal poor carbon enhanced stars, we find that there are hints of unique properties of the first stars that you don't see anymore today in the supernovae. There's various models that can explain this high carbon abundance. The details don't matter too much, but for example, you can have a faint supernova where you only get the outer layers of a star expelled, which is where the carbon is, but not the inner parts where the iron is. So you get a very high carbon over iron ratio. You can also make very high carbon if you have a very rapidly spinning star. And there's reasons to believe that the first stars were quite fast in the way that they were spinning. And this is unique things that don't happen in more metal-rich supernovae, but they were kind of inferring from the metal poor stars that we see today. So there's also some more metal-rich carbon-enhanced stars, and we've actually realized that they're not necessarily connected to the first stars, but they're connected to binary interactions. So they're stars in a double system where the star that is currently carbon-rich has actually gotten their elements from a dying low-mass star that has winds in which it's sending the carbon elements to this star today. So it wasn't born carbon-rich, but it became carbon-rich over their lifetime. And we can use the different elemental ratios to distinguish these different scenarios. So then all of this work is mostly focused on the normal halo of the Milky Way, where we have 20, 40 years of observations. And we're only just starting to look at the inner galaxy. And the questions are, is the frequency of these carbon-rich objects the same or not? If it's not the same, that means there was some difference in the building blocks that were making the inner galaxy. And with PIGS, we can actually measure the carbon abundance. And what we found as a function of metallicity, so in black is the frequency, so how the fraction of stars is carbon-rich below a certain value. And in green is that for the normal halo. And you can see there's actually a very big difference in these frequencies between the inner galaxy and the rest of the halo, although they get together more closely as you go to lower metallicities. As you remember, the lower metallicity ones were likely the ones that connected to the first stars. So maybe they're actually quite similar in the halo and the inner galaxy. But in this range, it's a very big difference. And that might tell us something about how many stars are in binary systems. Or actually, it might also, so this might be a difference in the first stars, pure binary systems. But it's also still an open question. Are we really comparing the same thing in the halo and in the inner galaxy? And are there any kinds of systematics that might produce this difference that is not actually real? And again, this is an open question that I think is really interesting because it tells us about both the first stars and something very different, which is the number of binary stars. So just a summary, what we can learn from the different elements. There's too much to cover in the inner galaxy, but overall, the abundances are not strikingly different from the normal stars. There are only small hints at differences. And overall, it's consistent with the picture that there were larger building blocks contributing to the inner galaxy than to the rest of the halo. But it is still this very chaotic phase that likely formed this component. So then what is next? We have lots of photometry, we have lots of dynamics, but we want a large sample of homogeneous chemical abundances for these stars in the inner galaxy. And this is going to happen over the next few years. There's a few big surveys that are starting. So we have Gaia already, which is giving us the distances and the space motions. So these surveys are going to give us thousands, hundreds of thousands, millions of spectra of stars all over the sky, including the center of the Milky Way. And this is a picture of the WEAVE instrument, and all of these little dots are positions on the sky where you're taking a spectra at the same time. So here you can take about 1,000 spectra at the same time, looking towards the sky. So this is going to be scanning the whole sky very efficiently, and we'll be able to compare all of the different regions with each other. So I'm very, very hopeful that that's going to be, life-changing for what we know about the bulge. So then just a short summary. So in this talk, the main theme is galaxy formation, specifically Milky Way formation, and what about these very early building blocks? How are we doing this? We're using very small stars that survived from the start of the universe till today. And we're probing the effect of really massive stars through the chemistry. So we're looking at stars of different metallicities, so kind of from older to younger stars, see a range in the Milky Way. And then we're finding with specifically the Pristine Inner Galaxy Survey that there's a big population of stars, these metal poor stars in the center on kind of random orbits. And then if you want to know a lot more, you go to the chemical abundances. So this is kind of a summary of a specific corner of galactic archaeology. There's a lot more you can do, and I'm happy to take questions. Thanks.
You want to have time for a few questions? Go ahead in the audience.
There's one do.
Okay.
Martin, thanks for that fascinating talk. The answer for a star to be old, it has to have been small. I thought it was hard to make a small star with low metallicity.
Yeah, it's a good question. So it's hard to make a small star with no metallicity. So if you have no metals at all, it's hard to make a small star. But as soon as you have a little bit, as soon as you have had one supernova, you can actually form these small stars because you have enough heavier elements that help to cool a cloud so that it can be dense enough for stars to form. So we think that there's kind of the first stars, and then everything else after that is kind of similar. But it's a little bit of an open question whether the masses of really molecular stars the distribution of them is very different from stars today. Yeah. Thanks for the question.
Yeah. So your research is in obviously from this sort of mission spectrum. Is it possible to study the core abundance of stars? Have a different story.
So you're interested in the composition of the cores of stars, is the question. Yeah. So you can't look at the core of a star. So all you can see is the surface. So something that has become possible in the past 10 years or so is to use something that's called astroseismology, which is looking at the kind of the vibrations of a star and the different vibrational modes of a star. And that actually tells you something about the inner structure of a star. So you can see these kind of pulsations in the brightness of a star. And that tells you something about the internal structure, which you can then infer something about the composition. Is there a lot of carbon in the core? It would vibrate differently. A little bit similar to what we do on the Earth to infer what's inside the Earth. Yeah.
Any more questions?
It's no dumb questions.
Is there any other research which focuses on other galaxies, which is Milky Way?
Yes. So the advantage of the Milky Way is that we're right here, and the stars are, we can actually observe the stars in a lot of detail. We can do this. So the Milky Way still has some small dwarf galaxies that are satellites that are going around. So they're kind of building blocks that never merged with the Milky Way, and you can do this kind of detailed analysis for these dwarf galaxies, and you can kind of compare, which confirms that the chemistry is different. So we can start doing this but only very, very superficially in the Andromeda galaxy, so the big neighboring galaxy of the Milky Way. You can get metallicities and maybe one other kind of type of element. Yeah, so it all kind of, that's the local bubble where we can do this. And then if you go beyond, you can use, you can take a spectrum of a galaxy, and then you kind of get the collective light of all the stars in a galaxy. But you can do some modeling to try to figure out, how many massive stars, how many low mass stars contributed, and kind of get the overall abundance of a galaxy as well. And you can do that in different regions if you kind of just do that for 2 or 3 or 4 regions in a galaxy. So you can kind of usually see that the halo is more metal poor than the disk, and that is across most galaxies. Yeah. Yeah.
So you're focusing on these smaller, older stars. So, but the ones with low metallicity, with the high metallicity ones, how do you get the metal in the first place? Because the stars would be so big, they might just perhaps
Yeah, so you can still form low mass stars today. So you can still form small stars. And if they form today, they'll have a high metallicity. So you can form small, high metallicity stars. So at every time in the universe, you can form small stars. So if you form a small star now, it will have high metallicity, and you can still measure the abundance of these elements. Does that answer your question?
Well, I really meant to see first very big stars. They might not spew out their elements to create stars with high metallicity.
You mean so the very first stars, they always have to explode. They can't live forever. So they will return their elements back. And then you can also have big stars forming today, and they will also explode again and enrich the universe even more. And then the next generation of stars that forms from that will be more metal rich. Yeah. Yeah.
With the color table picture, we actually tell which special bit in the physical process that producing these like specific elements.
Yeah, it's a very good question. And actually the exact ratios in this periodic table are not known exactly. So this is a big uncertainty so we know roughly which processes can form which elements, but not necessarily by which ratio. And yeah, I think there's still quite a bit of research in that area that needs to be done on nuclear physics calculations and stellar yield modeling and stellar evolution modeling, that it all depends on these different things. Yeah. Thanks.
You mentioned carbon transfer or elemental transfer
Yeah.
between different stars. Given that the stars in the central proto-galaxy area seem to get very close to the galactic center, have there been any models which suggest there may be an interaction between black holes and the stars which could cause some kind of transfer of these?
Yeah, that's a very good question. So kind of, could you disrupt binary systems in the center because they interact with the black hole or something like that?
Stars which were mass rich, look as full.
Yeah, so you can't really make a star look more metal poor than it is. You always gain elements, you always pollute. So these stars, they don't actually go that close to the black hole for it to really have an influence on the stars. But it is true that it's a much higher density environment. So you have a lot more stars going on. So it could be that for some reason these binary systems are disrupted more easily because it's just a lot more other stars that are going on as well.